Hey, everybody. Welcome back to Physics Computer Science 219A. This will be the fifth lecture of the fall term. As you may know, I've had a few technical glitches in the last couple of lectures. In fact, last time, by mistake, I turned off screen sharing. So for about half the lecture, you were just looking at my face without seeing my slides. But since I'm distributing the slides as a PDF file, I hope you were able to persevere by viewing the slides while listening to the lecture. And I think by now, maybe I've reached the point of having made most of the obvious mistakes. So I'm anticipating, I feel lucky today that we won't have technical glitches today. In fact, I even turned off my phone, so we won't have Siri butting in to tell us what she thinks she knows about quantum channels. So let's hope for a technically perfect lecture, although I'm sure the lecture itself will still leave something to be desired, but I'm doing the best I can. I hope you're enjoying the course. I'm having fun, but that's not really a fair test because I'm kind of easy to please and I love this stuff. But I hope you're learning something. So let's see. Now I'm going to be checking from time to time that I really am sharing the screen. I guess I learned my lesson on that, but I believe I am. So let's go. So this will actually be the last of our lectures introducing the theory of open quantum systems. Remember, we say a system is open if it's not perfectly isolated, if it can exchange energy and information with an unseen environment. We're interested in that because all real systems are open, at least to some extent. And we've discussed how in the setting of open quantum systems are axioms that characterize the quantum theory of closed systems need reconsideration. Quantum states of an open system are described by density operators in general. Measurements are not necessarily orthogonal measurements. They can be POVMs, generalized measurements. And last time we talked about how quantum states evolve when systems are open. That's described not by unitary maps as for closed systems, but instead by what we called quantum channels, also known as trace-preserving completely positive maps. And we discussed how a channel can be given a operator sum representation, also called a cross representation. And we discussed why physical operations that can actually be applied to quantum states should have the property of being completely positive. And last time we used an isomorphism between completely positive maps and states to show that completely positive maps always do have operator sum representation. So we can always imagine when we're talking about a quantum operation that what's really going on, whatever really means, is that there's an extension of the system to include an environment and that a unitary map is being applied to our system and the environment where initially the system environment are uncorrelated in a product state, and then we trace out the environment to get the result of the map. This point of view is sometimes honored by the name of the Church of the Larger Hilbert Space, that we can always use our closed system point of view if we imagine extending the quantum system as the gist of that ideology. So what I want to do today is continue one more lecture with open systems by fleshing out what we learned last time about quantum channels. The discussion last time was quite general and abstract. That's okay. I like general arguments. They can be very powerful. But it's also important to fully appreciate the general theory to see how it applies to some examples. So what I'll mostly talk about today are some examples of quantum channels. And to keep things simple, I'll consider quantum channels just acting on a single qubit. on a two-dimensional Hilbert space. And the examples will, I think, be instructive, apart from deepening our understanding of the general theory of quantum channels. They also have some lessons that are of physical interest. So let's start. So the first example of a quantum channel that I'd like to discuss is called the Depolarizing Channel, acting on a qubit. This channel is special because it's sort of the most symmetrical of quantum channels. It doesn't pick out any preferred direction in the Hilbert space, in a sense. And we can think about the depolarizing channel for a qubit in the following way. You remember our notation for Pauli operators, which sometimes I've called sigma 1, sigma 2, sigma 3. Here I've used the alternative notation, x, y, and z. And what happens when a quantum system, when a qubit is subjected to the depolarizing channel, we can think about it this way, that there's some error probability p, a probability p that something happens to the qubit. So with probability 1 minus p, nothing happens. But with probability p, one of three possible errors occurs, which changes the quantum system. I'm imagining that, we'd like to preserve our qubit in a memory, and so I'm speaking of an error as something that changes it, so it becomes damaged, and it's not the original state of the qubit that we stored in our quantum memory. And those three possible errors are all described by Pauli operators. And the three Pauli operators, denoted here x, y, and z, are all equally likely. So each occurs with a probability p over 3. So the total probability of a Pauli error is p. And the three types of errors we can think about this way. The Pauli operator x flips basis state 0 to the basis state 1 and 1 back to 0. Well, that's just like a bit flip that occurs on a classical bit. So I can think of the x as a bit flip error. The z I can think of as changing the relative phase of the basis state 0 and 1. Or if you like, I can imagine an alternative basis, which we talked about before, the basis states plus the uniform superposition of 0 and 1, and minus the orthogonal state, the superposition 0 minus 1. And because it changes the relative phase, the relative sign of 0 and 1, what a z error does is it flips a plus to a minus and a minus to a plus. And y up to a phase factor is just the product of a z and an x. So you can think of that as the error that simultaneously applies both a bit flip and a phase error. So we can describe this channel, like we can any channel, in terms of some set of Krauss operators. And for this channel, I can choose the Krauss operators to be the four that I'm showing here, called M0, M1, M2, and M3. So M0 is the Krauss operator that corresponds to the possibility that nothing happens to the qubit. So that's proportional to the identity. It doesn't change the state. And it has a coefficient, which is the square root of the probability with which that operation occurs, namely the square root of 1 minus p. And then for our three other Krauss operators, which do correspond to errors that affect the qubit, they are respectively proportional to Pauli operator x, y, and z, and all have a coefficient which is the square root of the probability of that error, which in this case is the square root of p over 3. So now if we think about our operator sum representation, remember how it works. The channel acting on an input density operator is going to be the sum of four terms, which is, in this case, all of our operators are Hermitian, so I don't have to worry about the difference between M and M adjoint. So I have M0 rho M0, and M0 is proportional to I. So that just gives me 1 minus P times rho, the input density operator. And then I have M1 rho M1, M2 rho M2, and M3 rho M3. So each one of those will be proportional to P over 3, the probability of the corresponding error. And then I get the sum of X rho X. That means X error occurs on the state, Y rho Y, a Y error, and Z rho Z. Now these Pauli operators all have the property that they square to 1, so we can check easily our normalization condition for the cross operators. This is the condition that the result of applying the channel to input density operator rho, if rho has unit trace, if it's properly normalized, so will be the result of applying the channel to rho. And well, if we just take the sum over A of MA adjoint MA, in this case, MA is self-adjoint, so MA adjoint is the same as MA. That's supposed to be equal to the identity. That's the condition that the trace is preserved. So from M0 squared, I get 1 minus PI. And for the other three terms, I get P over 3 times I. And because there are three terms, that adds up all together to P times I. And the sum of all MA adjoint MAs is then just the identity, as it should be. Or we can see the same thing coming back here. If we just take the trace of the right-hand side of this equation, it's the trace of a sum, which is the sum of the traces. So here I get 1 minus P times the trace of rho, which is 1 minus P. And when I take the trace of X rho X, of course, the trace is cyclic. So I can move one of the X's over to the other side. X squared is equal to the identity. So each one of these terms gives P over 3 times the trace of rho. There are three such terms. And so I wind up with 1 minus P plus P times the trace of rho, which is 1. Now, remember we talked about this idea of channel state duality. And let's see that in action for the depolarizing channel. The way it worked was we imagined preparing a maximally entangled state of the qubit on which our channel is going to act and a reference system. And then we considered the channel acting only on the qubit, not on the reference system. So let's see how that works here. I'm going to choose as the initial state, the entangled state of our system and the reference system, this state phi plus. It's a superposition of 0, 0, 0 for system and 0 for reference, plus 1, 1, and I've normalized it. And I'm also going to consider four other states, which are all entangled. They're all maximally entangled, meaning that in all of these states, if I trace out the reference system, the density operator for the system is just maximally mixed. It's 1/2 times the identity. And they're all mutually orthogonal. So we can think of these entangled states as a basis for the four-dimensional Hilbert space consisting of our system and reference system. And the other states in this basis are 0, 0, minus 1, 1, 0, 1 plus 1, 0, and 0, 1 minus 1, 0. It's easy to see they're all mutually orthogonal. And well, you can check that. So now to find the state that under the isomorphism between states and channels corresponds to our channel, what we are to do is to take this maximally entangled state phi plus. I'm here looking here at the corresponding density operator, the projection onto phi plus, and I let the channel act on the first qubit and the identity act on the second. Okay, so with probability 1 minus P, our channel doesn't do anything. So I still have the pure state phi plus. But then with probability P over 3, each of three possible things can happen, an X error, a Y error, or a Z error. So what happens if I apply X to one of the qubits and not to the other? well then 0, 1 plus 1, 0 is going to become 1, 0 plus 0, 1. That's another one of our basis states, what I called psi plus. So when I have x acting on the left and on the right, this ket phi plus, bra phi plus becomes ket psi plus, bra psi plus. And if I consider z acting on one of the two qubits, the first qubit, say, in phi plus, that's going to change the relative phase of the 0 and the 1. So that's going to map phi plus to what I call phi minus. It becomes 0, 0 minus 1, 1. And so we also have a term here in which the projection onto phi plus has been mapped to the projection onto phi minus. And then the third possibility is the y error, also occurring with probability p over 3. And because that both flips a bit and changes the phase, it maps phi plus to the state here that I called psi minus up to a phase. And that phase isn't going to matter when we can correspond when we look at the corresponding density operator. So under the y error, projection onto phi plus gets mapped to projection onto psi minus. Now, notice there's something special about the case p equals 3/4. That's the case in which the error occurs with a total probability of 3/4. So in other words, an x error, a y error, and a z error all occur with probability 1/4. And the case where nothing at all happens also occurs with probability 1/4. So in that case, when we let our channel act on the first qubit and the identity on the second, the maximally entangled input state, this projection onto phi plus, becomes this equally weighted mixture of our four basis states. I get 1/4 the pure state phi plus, the pure state psi plus, the pure state psi minus, the pure state phi minus. And remember, these are the orthonormal basis states, or a choice of the orthonormal basis states for the two qubit system. And so this is just the maximally mixed state for that four-dimensional space. It's 1/4 times the identity acting on the pair of qubits. Now, if you remember how our relative state method works, we can apply it here to see how the channel itself acts on a desired input state. Now, you remember I did a funny thing when I defined this relative state representation. I didn't actually consider the input state to be phi plus, but rather an unconventionally normalized state, just the 0, 0 plus 1, 1 without the 1 over square root of 2. And so in this case where the error occurs with a total probability of 3/4, that unconventionally normalized state actually gets mapped not to 1/4 the two qubit identity, but rather 1/2 times the two qubit identity. And I did that because then we have a nice characterization, a nice formula for how the channel acts on just a single qubit. If I want to know for an input pure state psi, what the channel does, what the relative state method tells us to do, is to take this state, the output from the channel, except for this funny normalization, when the input is phi plus of system and reference system, and that in this case is just 1/2 times the identity, and then I take its expectation value in a state psi star, which is just psi except with its coefficients and our particular 0, 1 basis complex conjugated. But because it's just the identity in psi star is a normalized state, that's just 1/2 the identity for the output qubit from the channel. So what that's telling us is that in the case where the total error probability for the depolarizing channel is 3/4, any state you put in particular, this pure state psi, is going to be mapped to the maximally mixed state, to 1/2 the identity. And of course, the same will be true for any mixed state, because a mixed state is just a mixture of pure states, and the channel is linear. So the depolarizing channel in that case, with p equals 3/4, is a special type of channel. In effect, it throws the state away and it replaces it by a maximally mixed state, by an essentially random state in our Hilbert space. In that case, we say it's completely depolarizing. If you think about the Bloch sphere picture, which we've talked about last time, or maybe I guess it was the time before, the pure state lives on the Bloch sphere itself, on the boundary of the Bloch ball. The maximally mixed state lives right at the origin of that ball. And what this channel does when p equals 3/4 is it takes any state, in particular any pure state, to the center of the ball. And in other words, it completely destroys the polarization of the qubit. And that's why I'm calling it completely depolarizing. Okay, but now that was just for the case where p is equal to 3/4. What about general values of p? Well, let me do the following thing. We already saw how the channel tensored identity acts on the maximally entangled state of our system and a reference system. But now I'm going to add to the term we had before, which had projection onto psi plus, onto psi minus, and onto phi minus. I'm going to add to that projection onto phi plus. And I want to do that because I know that's just the identity operator acting on that 2-qubit system. And but then I made a little mistake when I put projection onto phi plus here, so I have to subtract it away here. So where before we had 1 minus p times the pure state phi plus, now that's going to be 1 minus 4p over 3 because I added p over 3 times projection onto phi plus over here. And let's get my little face out of the way. There we go. But now this is just the identity. The maximally mixed state is 1/4 times the identity for the 2-qubit system. So let me factor out that 1/4. And so now the coefficient of the maximally mixed state here is 4p over 3. So in the case where p is no larger than 3/4, we can think about our depolarizing channel in the following way. It's just as though, before I said, well, we either do nothing or we apply X or we apply Y or we apply Z, each equal probably. But there's an equivalent way of describing what the channel does, as we now see. With probability 1 minus 4p over 3, nothing happens. And then with probability 4p over 3, we throw the state away and replace it by a maximally mixed state. That's just another way of saying what's going on. Now, what about the Bloch sphere picture? You remember the Bloch sphere? I just made a reference to it a minute ago. This is supposed to be a picture of the Bloch sphere. It's a unit sphere. You remember, associated with the density operator of a qubit is a polarization vector. We can write the density operator with no loss of generality for a qubit as 1/2 the identity plus, here I've written it as vector p dot vector sigma. That means p1 times x plus p2 times y plus p3 times z. All x, y, and z are all traceless, by the way, so we can see that the trace is properly normalized here. The trace of identity is 2, so the trace of rho of p here is 1. And from the point of view that I just described, where either we do nothing, so rho of p is unchanged, or with probability 4p over 3, we replace the state by the maximally mixed state. In the case where I replace it by the maximally mixed state, I just get a number times I. The important thing is that when the error occurred, the case of no error, when we didn't throw the state away, that occurs with probability 1 minus 4p over 3. So the effect of that is to rescale the polarization by the factor 1 minus 4p over 3. And you can think about it that way, even when p is larger than 3/4, although in that case, you'll notice the polarization kind of gets turned inside out. When p is equal to 3/4, it sinks right to the origin of the Bloch ball. And when p is greater than 3/4, it actually gets extended further to the other side. But anyway, if you want to think about how the depolarizing channel acts on a qubit, it's helpful to visualize it in terms of the Bloch sphere. And what happens is that all the pure states which live on the unit sphere in 3 dimensions get shrunk down to a smaller sphere. The polarization gets isotropically rescaled. The whole sphere deflates to, it's still a sphere, but now a smaller sphere. Now you could ask, well, suppose I wanted to undo the effect of the depolarizing channel. I would just have to blow the Bloch sphere up again to reverse the deflation that occurred. But remember, we said that except in the case of a unitary map, completely positive maps can't be inverted by physical completely positive maps. And you can see how that works here. If I want to undo the effect of the depolarizing channel, I want to inflate the sphere to a larger sphere so we can go back up to unit radius. But if I rescale the polarization by a factor larger than 1, that can't be a physical map because it takes physical density operators, which had the length of the polarization vector less than 1 or equal to 1, to unphysical states, which have a polarization vector larger than 1. And those are not positive operators, okay? So we can't undo the depolarizing channel, and it's kind of nice to have a geometrical way of thinking about that in this case. We know in general there isn't a physical operation that can undo the effect of decoherence, undo maps which are not unitary. All right, now I want to talk about another example of a qubit channel. And in this case, let's think about kind of a physical picture of what might be going on. I want a very simplified model, kind of stripped down to the essential features of the following physical situation. There's a little piece of dust. It's floating around in intergalactic space, but it's quantum dust. So it doesn't necessarily have a well-defined position. It might be in a coherent superposition of different possible spatial positions. And let's suppose there are 2 possible places it could be, and I'll label those 2 states by 0 and 1 because I'm not very imaginative when it comes to labeling basis states of qubits, and I call them 0 and 1 in most cases. But in this case, we're envisioning that 0 and 1 correspond to 2 possible positions for the dust grain, which could be in some superposition of those 2 positions. But the dust grain isn't perfectly isolated because there are some photons drifting around. They're the 2.7 degree photons maybe that are left over from the Big Bang. Those are everywhere, even between galaxies. And every once in a while, a photon might encounter our grain of dust and be scattered by it. But the way the photon gets scattered depends on the position of the dust grain. So the picture I would like to suggest is the initial state of this photon, which is incident on the dust grain. I'm going to call 0. And then it scatters. And it scatters into either one of 2 distinguishable states. If the dust grain is in the position that I'm calling the state 0, then the photon gets scattered to a state 1. And if the photon encounters the dust grain in the state 1, if it's in the position corresponding to what I'm calling state 1 of the qubit, then the photon scatters to some other state 2. And I'm going to take 0, 1, and 2 to all be distinguishable or orthogonal possible states of the photon. But this process is a unitary process, okay? Everything's described quantum mechanically. And what happens is that because of this scattering, the photon becomes correlated with the dust grain. The state of the photon will either be 1 or 2, corresponding to whether the dust grain is either in state 0 or 1. So the unitary process in which the photon interacts with the dust grain is going to create an entangled state, potentially, of the dust grain and the photon. So we can describe that by a map. I'm calling it here an isometric map. That just means that it preserves inner products. And I'm making kind of a distinction, which is a bit pedantic. We've talked a lot about unitary maps, but in this case, I'm not going to worry about, well, I'm not going to keep track necessarily, I could have, of the initial state of the photon, and I'll just worry about if I have the initial state of the dust grain to be either 0 or 1, after the encounter of the photon, what is the joint state of the dust grain and the photon? And because that's mapping 1 qubit to 2 qubits, it's not really unitary, but it's isometric, meaning it preserves inner products. So it's something that, that physically makes sense. So in the case where the dust grain is in the state 0, after encountering the photon, the state of the photon, I'm using E to suggest environment, A is our system, the dust grain, it's in some superposition of 0 for dust grain, 0 for photon, because there hasn't been any scattering and the state of the photon didn't change in that case, and 0 for dust grain and 1 for photon, okay? And the coefficients I'm going to call the square root of 1 minus p and the square root of p. Of course, they're squares. I have to sum up to 1 because the state is still normalized. Well, if on the other hand, the state of the dust grain were 1, then I'm going to suppose that again with the same amplitude as before, the square root of 1 minus p, there is no scattering. The photon doesn't encounter the dust grain. But in the case where there is scattering, now the photon is going to be scattered from the state 0 to the state 2. And so in the case when the dust grain was in the state 1, after the interaction with the photon, I have this state, the square root of 1 minus p, state 1 for dust grain, 0 for photon. That's the case where no interaction occurred, there was no scattering, plus the square root of p, 1 for dust grain, 2 for photon. That's the case in which the photon got scattered into the state 2, into a state distinguishable from the initial state and also distinguishable from the state that it winds up in if the dust grain had been in state 0 instead. So now I can describe this in terms of cross operators. Remember, you can always imagine that we perform a measurement on the environment. In this case, I'm going to measure the photon or imagine measuring the photon in the 0, 1, 2 basis. And associated with the 3 outcomes, the photon is in the state 0 or 1 or 2. There are 3 cross operators which act on the state of the dust grain. In the case where the photon is in the state 0, that's the case in which nothing happened to our qubit. So the cross operator is just the identity, and it has inherited this square root of 1 minus p. In the case where we measure the photon and find it in the state 1, well, that means we must be looking at this component of the state. So that couldn't have occurred if the dust grain had originally been in the state 1. So what I actually have is a projection onto the state 0 of the dust grain, and this square root of p becomes the normalization of my cross operator. And in the case where I measure the photon and the outcome is the state 2, that means that that's coming from here. So that means that the dust grain must have been in the state 1. It gets projected onto the state 1, and again with this amplitude, square root of p. Now it nobody had to really measure the photon or detect the photon with some kind of detector. We can just do the trace over the unobserved environment, in this case, the photon and any basis we want, and it was convenient to do that tracing out using the 0, 1, 2 basis, and that's how I arrived at these three cross operators. Remember, you always have the freedom to change the basis of that measurement, and that corresponds to some unitary remixing of the cross operators. Now, in fact, you can see that the cross operators are not, in this case, linearly independent, because if I add together M1 and M2, I get something proportional to the identity. So this was a convenient choice for cross operators because it corresponded very directly to the way I was thinking about this physical process, but it's not a minimal representation of the channel. We're using one more cross operator than we needed to because they're not really linearly independent. Or to say it another way, I can express all of the three cross operators, M0, M1, and M2, as linear combinations of two operators, namely the identity and the Pauli operator Z. Because, well, this is the identity, M0 is the identity, but also the identity plus Z is the matrix 2, 0, 0, 0. It has 2 only in the upper left, zeros elsewhere. And identity minus C is the matrix which has a 1 in the lower right and the other elements equal to 0. So I wrote 1 here, but it should be identity. That's a little confusing. Maybe I'll fix that. But at any rate, let's rewrite our channel by rewriting our cross operators in terms of identity and Z. So again, with probability 1 minus P, nothing happened. But then with probability P, I have a 1/4 here because remember when I took 1 plus Z, that was actually twice this matrix. So I divided by 2 and then I wound up squaring that because I have an M1 on the right and the left. So I have P over 4 here. And then identity plus Z, rho identity plus Z, that's the M1 term. And then for the M2 term, now I'm writing my cross operator as the square root of P, which got squared here, times 1/2 identity minus Z. So multiplying this P over 4, I have identity minus Z, rho identity minus Z. And now we can simplify this a little bit, because the terms here which have a Z on one side and the identity on the other, they're going to cancel because they occur with the plus sign and they occur with the minus sign here. And so since those terms cancel, all I wind up with are the identity rho identity terms, and there are 2 of those. So the P over 4 became a P over 2, and the 0 Z terms. And because these 2 minus signs cancel, those add together and they give me P over 2 0 Z. So if I combine together this row with this row, there's another way of describing the channel, which is a completely valid way of describing mathematically what it does, which is with probability P over 2, an error occurs, namely a Z is applied to the state, and with probability 1 minus P over 2, nothing happens. So you see, there's a difference, an interesting difference here for this channel, which I'm calling the dephasing channel, which is there's a special basis that it picks out, namely the 0, 1 basis. That wasn't true for the depolarizing channel. It didn't really have any preferred basis, and correspondingly, we could see that it deflated the Bloch sphere isotropically. But here, there's a preference for the Pauli operator Z, or for its eigenbasis, consisting of the state 0 and 1 for the dust grain. Now let's go back to the original 3 cross operator representation, because that's kind of convenient for seeing how a density operator of a qubit is affected by this channel. So suppose there's some input density operator, completely general. So I've just written it this way. It's actually, as you know, a Hermitian trace 1 non-negative operator. And this notation doesn't show that explicitly, but that's okay. It just has entries, row 0, 0, and row 1, 1 on the diagonal, row 0, 1, and row 1, 0 off the diagonal. And so if you look at what these operators do, when we square this guy, in other words, when we consider M0 row M0, that's just going to multiply the whole density operator by 1 minus P, both the diagonal and the off-diagonal parts. But then the guy M1 then adds an entry which is P row 0, 0, because this is projecting out the 0 component, and M2 is projecting out the 1 component, so that's going to give me a P row 1, 1. So on the diagonal, I wind up restoring the original entries when the channel acts. So row 0, 0 and row 1, 1 are not affected, but the off-diagonal terms are affected. They become smaller. That's a kind of loss of coherence. I'll try to make it a little clearer what that means in the next slide or two. But anyway, again, this is reflecting the special basis that our dephasing channel picks out. We're representing the density operator in the 0, 1 basis. And in that basis, the off-diagonal terms are suppressed by the channel. The on-diagonal terms are not affected. And of course, the trace is preserved. Now, we might think about what's going on this way, that there are many photons, and many photons are incident on our dust grain. And for each one, it's highly probable that there's no scattering at all. So the term in which nothing happens dominates in each scattering event. But there are many scattering events. So over time, the density operator is affected by the interaction with the photon. So let me think about that this way. There's a number P, which we saw we could think of as the probability that a scattering occurred when the photon encounters the dust grain. But because there are many photons encountering one after another the dust grain, let's think about that as a probability per unit time. Or suppose there's a very small time interval over which we're monitoring the dust grain, which I've called delta t, and that the probability of a scattering event, of the photon being scattered into a state which is orthogonal to its initial state, is proportional to the time for small times. So it's just going to be some number times gamma t. P is a dimensionless number, so gamma has the dimensions of 1 over time. I'm calling gamma that probability of a scattering event of an error per unit time, and I'm imagining that delta t is small enough that that probability is a small number. But now suppose I consider many such tiny time intervals, so the total time that elapses is n times delta t, where n is a large integer. Then this channel is actually applied many times in succession. Every time a photon comes by, it comes by each time interval delta t, let's say. So in time n delta t, the channel has been applied n times. And each time it's applied, the off-diagonal terms in the density operator get hit again by another factor of 1 minus p. So after n applications of the channel, the off-diagonal terms have been suppressed by 1 minus p to the nth power. And now p, remember, is this gamma delta t, the small probability of scattering in each scattering event. And now I'll write that in terms of the total time. It's gamma times the total time that's elapsed divided by n, the number of small time intervals, and that got raised to the nth power. And then if I consider letting n get large, then this just approaches an exponential e to the minus gamma t. So in other words, as a function of time, the off-diagonal terms in the density operator decay exponentially with time. Or here's another way of saying what I just said. when we apply this channel n times in succession in the limit I just considered, the on-diagonal terms are not affected, but the off-diagonal terms decay by a multiplicative factor, which is e to the minus gamma t. So if gamma t gets to be a large number, in other words, if the time gets large compared to 1 over gamma, then the off-diagonal terms become negligible. And if we started out with some coherent superposition of our qubit, if we imagine the dust grain was in a superposition of two possible positions with coefficients a and b, then after a sufficiently long time compared to the so-called coherence time, 1 over gamma, that density operator has decayed to a mixture. It has some probability, absolute value of a squared, of being in the state 0, some probability, absolute value of b squared, of being in the state 1, and there any possibility of interference between the 0 and the 1 has been completely destroyed by this process in which the photons scatter off the dust grain. So again, we see that there's a preferred basis for this process, that the dust grain decoheres in the 0-1 basis as a result of the coupling to the photon that we describe. So that's what I mean by the basis dependence. You know, I say, oh, well, this coherent superposition is going to decay to a mixture, but, you know, how do I know that it's going to be a mixture of 0 and 1? Why isn't it a mixture of 0 plus 1 and 0 minus 1? Okay, well, it's because of the way the photon is assumed to interact with the dust grain. And in particular, we've sort of built in some locality assumption that the state of the photon after the scattering is going to be different if the dust grain is in the position on the right than it would be the position on the left, because of the locality of the nature of the interactions between the photon and the dust grain. You know, you could have asked a similar question about that poor cat of Schrodinger's, which is in a linear combination of alive and dead. And then it decoheres, we like to say, very quickly. It's either definitely alive or definitely dead. It behaves like a mixture of alive and dead instead of a coherent superposition. That's because of a similar process. It's because the cat interacts with its environment, just like this dust grain interacted with the photon. And for a similar reason, there's a preferred basis. It doesn't decohere in the basis alive plus dead and alive minus dead. It decoheres in the basis alive and dead because of the nature of the interactions of the environment with the system, in this case, the photon being scattered off the dust grain. Now, we can also visualize this process from the Bloch sphere point of view. So now let's go back to the other way of describing the channel, which is that with probability p over 2, the Pauli operator z is applied to the qubit, and with probability 1 minus p over 2, nothing happens. So since that z commutes with z, it commutes with itself, of course, it doesn't affect the third component, the z component of the polarization of the qubit. That just stays the same. But x anti-commutes with z, and y anti-commutes with z. So in other words, zxz is equal to minus x. zyz is equal to minus y. So if I ask what happens to the other components of the polarization, the x and y components, again, with probability 1 minus p over 2, nothing happens. But with probability p over 2, that component flips. X goes to zxz. And so you put together those two contributions, and for either the x or y polarization, or the 1 or 2 component of the polarization vector, it gets depressed by the multiplicative factor 1 minus p. So visually, what's happening is that along the z direction, the polarization is unaffected, but in the X and Y directions, it's deflating. And so it becomes a prolate ellipsoid, kind of a football shape over time. And as the time gets longer and longer, if I think of, the channel that I just described in which the dephasing event occurs over and over again, it will shrink to a narrower and narrower ellipsoid, eventually asymptotically occupying the z-axis, where the 1 and 2 components of the polarization have been completely eliminated, but the z component is unaffected. Now you might wonder, well, what kind of channel would cause the Bloch sphere to evolve not to this prolate ellipsoid, but instead an oblate ellipsoid, a pancake shape? And the answer is that doesn't happen, because that's not really a physical, completely positive channel. If you think about it, well, in some appropriate basis, what that would mean is that P2 is shrinking, but P1 and P3 are not. But that map is really the transpose map, okay, that we talked about before, because remember that the Pauli operator Z and the Pauli matrix X are both symmetric matrices, while Y is an antisymmetric matrix. So under the transpose, X and Z are unaffected, but Y goes to minus Y. So that map that gives rise to a pancake instead of a football is one in which a transposition occurs with some non-zero probability. And that's not completely positive. So that's the no pancake theorem. You don't see the Bloch sphere shrink to a pancake localized at the equator, although it can shrink to a football localized on an axis. Now, this type of dephasing is seen in many different physical systems. And one can, in the laboratory, measure this dephasing rate, gamma, observe the exponential decay of the polarization. Then example might be, I prepare a state of an electron spin. Maybe it's a superposition of spin up and spin down, or an atom in a optical trap, which is a superposition of the ground state and the excited state, where the two states that are being superposed have different values of the energy. In the case of the electron spin, that might be because it has a magnetic moment and it's in a magnetic field, so spin up and spin down have different values of the energy. So in the basis in which it's diagonal, the Hamiltonian has two distinct eigenvalues. By fixing the zero of energy, I can make one of those eigenvalues 0. So the Hamiltonian, I don't usually write H bars, but I guess here I decided I would. But usually I've said H bar equal to 1, which I did without comment, because it's really not important to us, for the most part, in this course, what the value of H bar is. So let's say the state 0 of our qubit has 0 energy, but the state 1 is an excited state with some positive energy omega. Then if I don't worry about dephasing, if there's no decoherence, I'm just solving the Schrodinger equation, then the excited state in a time t picks up the phase e to the minus I omega t. The ground state is unaffected by the time evolution. And so if I prepare an initial state, which is a uniform superposition of 0 and 1, it will then oscillate. It will precess, if you like, around an axis. It will move around in a circle in the space spanned by 0 and 1. But if we include the dephasing as well, then there will be exponential decay of the off-diagonal terms in this basis, assuming, as is often the case, that dephasing is occurring in the energy eigenstate basis. So let's say it's an electron, which is a superposition of spin up and spin down. the environment might be able to detect the difference between an electron with spin pointing up along the magnetic field axis and the electron with spin pointing down, because there are other spins in the environment, maybe other electrons or nuclear spins, which interact with the electron spins because all the spins have magnetic moments. And so decoherence will occur in the energy eigenstate basis. And so the evolved density operator will have the behavior I've shown here. There will be an oscillating off-diagonal factor, but it will be suppressed by this exponential decay term when t gets large compared to 1 over gamma. So if I prepare an initial state, and then I let it evolve for a while, and then I measure in a basis, which is the 0 plus 1 and 0 minus 1 basis. So I started out at time 0 here with 0 plus 1 up to normalization. I let some time pass, and then I measure to see whether it's 0 plus 1 or 0 minus 1. Did it go back to where it was originally, or did we wind up finding the orthogonal state? Then the probability of getting the outcome plus, that's just the matrix element in the state plus of rho of t. And remember, I'm talking about plus being 1 over square root of 2, 0 plus 1. So what this does is it just gives me 1/2 from squaring that 1 over the square root of 2 times the sum of the 4 entries in this 2 by 2 density operator. And of course, that means I get 1 plus 1 plus e to the minus gamma t to the I omega t, e to the minus gamma t to the minus I omega t. Adding together the e to the I omega t and e to the minus I omega t gives me twice the cosine. So we wind up with, up to the normalization factor, 1 plus the exponential decay times the cosine of omega t. So as time passes, the probability of getting the outcome plus will oscillate in time, but it will also be modulated by an exponential decay factor. And so I could measure that. The way I would do it is I'd repeat the experiment many times of preparing the initial state, 1 over root 2, 0 plus 1, waiting for some time t, and then measuring. And I would do that for many different choices of the time. And for each time, I would perform the experiment many times so I could estimate an expectation value by averaging the results. And in that way, I could get a plot like this one, where I can see the probability of getting the outcome plus as a function of time. It oscillates, but it also is governed by an exponential decay envelope. So from that data, I can measure both omega, which determines the period of the oscillation, and also the dephasing rate gamma from the exponential decay. Now I want to talk about another example of a qubit channel. I'm going to call this one amplitude damping. Another name for it is spontaneous decay. Let's imagine we're talking about an atom in this case. If that atom was in an excited state, it has some amplitude for emitting a photon and decaying to a lower energy state. So let's just consider an atom which has just 2 levels to keep things simple. So it's a qubit. We'll call 0 the ground state, 1 the excited state, the higher energy state. So the process by which the qubit can change is one in which we start out in the excited state, a photon is emitted, and a transition is made to the ground state. So in the language we've been using, our atom is interacting with an environment. The environment is the electromagnetic field. And to begin with, it's just in the vacuum. That means there are no photons around at all. But after some time, there might be a transition from the excited state to the ground state from 1 to 0. And when that happens, the state of the electromagnetic field changes. Now there's a photon there. In principle, I could detect that photon if I had a good high efficiency photodetector. So again, I should think of this as a unitary process, a unitary interaction between our two-level atom, a qubit, and its environment, the electromagnetic field. And to simplify things to what's essential, I'll consider the electromagnetic field to also be a qubit. It has just two states: the vacuum, there's no photon, and the one photon state in which a photon has been emitted. Those two states are perfectly distinguishable. They're orthogonal states of the electromagnetic field. Likewise, the ground and excited states of the atom are the basis states for a qubit, orthonormal states. So I can think of the process this way. If the atom is in the state zero, the ground state, nothing's ever going to happen. So it stays in the ground state, and the photon never appears. Photon, the electromagnetic field stays in the vacuum, the no photon state. But if we start out with no photon in the electromagnetic field and the atom in the excited state, then there is some amplitude for nothing to happen. So the atom is still in the excited state and there's still no photon, but it's possible for the excited state to decay to the ground state, in which case the atom makes the transition from the state 1 to the state 0, and the state of the environment changes. A photon appears. So the electromagnetic field is now in a state orthogonal to the initial state 0. So as usual, I can get cross operators by imagining measuring the environment in some basis and asking what the conditional state is of the atom for the different possible measurement outcomes. So in this case, there are two possibilities. If I were to measure the environment, either there's no photon or there's one photon. When there's no photon, that means that if we were in the state 0 of the atom, then nothing happened. But if we were in the state 1, it got suppressed by the factor, whoops, what happened here? It got suppressed by the factor square root of 1 minus p. That's the square root of 1 minus p here. And if I get the outcome 1 when I measure the environment, if I see a photon is there, then I know what must have happened was that the atom was initially in the excited state and it wound up in the ground state. And that's this cross operator, which just describes a transition from the state 1 to the state 0. And it involves the amplitude square root of p, which came from here. So let's look at what this channel does. Here's its operator sum representation. These are the two cross operators. In the case where the cross operator is M0, the M0 row, M0 adjoint term is going to suppress the 1,1 component of the density operator by the square of this square root of 1 minus p. So there's a 1 minus p here. But the off-diagonal terms get hit by just one of these square root of 1 minus p factors. So they both get suppressed by the square root of 1 minus p, and the 0, 0 component isn't affected. And then there's an additional contribution from the case where the photon is emitted. That's the cross operator M1. And what that does is it projects out the atom being in the state 1 to begin with, because otherwise it couldn't have decayed, but then the state 1 goes to the state 0. So the final state of, in the case where we detect the photon, has, oh, look, this should have been row 0, 0. No, that's not right. I'm sorry. No, it's row 1, 1. What had originally been the population or the probability of being in the 1 state, which is row 1, 1, that becomes this additional probability after the photon is detected of being in the ground state, which is proportional to row 1, 1 and also to p, the probability of the decay. So here I've just added those two terms together again, augmenting the row 0, 0 up here in the upper left entry, the density operator with the additional term p row 1, 1. And so what we can see is that this spontaneous decay process, what I'm calling amplitude damping for some reason, has an effect on both the on-diagonal and the off-diagonal entries. And there's a relationship between what happens off the diagonal and on the diagonal. In particular, the probability of being in the excited state gets suppressed by 1 minus p, and the off-diagonal terms get suppressed by the factor square root of 1 minus p. So now let's, as we did before when we talked about dephasing, consider watching the atom, or considering how its state changes over an extended period of time. So let's again imagine there are many consecutive time intervals, each of which is described by this channel, which I've just rewritten here. It's what we just saw a minute ago. And so the probability of the spontaneous decay occurring, if the state is in the excited state, has some rate, gamma per unit time, and the probability in a time interval delta t is gamma times delta t. And now, if we weight all together, same story that I told you a minute ago about dephasing, for n such time intervals, so the total time is n times delta t, then the 1 minus p suppressing the 1, 1 component of the density operator becomes 1 minus p to the n. But p, remember, is just gamma delta t. I can also write that as gamma t over n, if t is equal to n delta t, if they're all together n intervals, each of with delta t in time, that gets raised to the nth power. And if I consider the limit in which n gets large, if you like, in which I consider that tiny time interval delta t to be arbitrarily small, it's an exponential, e to the minus gamma t. And that same remark I just made in reference to the 1, 1 component of the density operator applies just as well to the off-diagonal ones, except now we get a square root of 1 minus p raised to the nth power. That's just the square root of the suppression factor that we have for the 1, 1 component. So when you put it all together, if we start out with an initial density operator with entries rho 0, 0, rho 0, 1, rho 1, 0, and rho 1, 1, after time t, the 1, 1 component has been suppressed by the exponential factor e to the minus gamma t. The off-diagonal components 0, 1, and 1, 0, both suppressed by e to the minus gamma t over 2. And well, then you can see what happens to the 0, 0 component just by knowing that the trace has to be preserved. So the trace of this matrix has got to be rho 0, 0 plus rho 1, 1, because that's what it was to begin with. And that tells me that this entry had better be rho 0, 0 plus 1 minus e to the minus gamma t times rho 1, 1. So that is what happens to our atom as we wait a long time for it to spontaneously decay. So there are a couple of things that are interesting to point out. So first of all, there's a relationship, as we previously noted, between what happens to the 1, 1 component, describing the probability of being in the excited state, and the off-diagonal components. And the standard language used in experimental physics is that the characteristic decay time for the excited population is called the T1 time. So we call this exponential factor e to the minus t over capital T1. Capital T1, that spontaneous decay lifetime, is just 1 over gamma. But there's also dephasing, like in our dephasing channel we discussed earlier, suppressing the off-diagonal terms, and that's just the square root of what we had in the 1, 1 component. And the standard terminology for the characteristic decay time for the off-diagonal components of the density operator is T2. So I can write this as e to the minus T over capital T2 is just twice T1. So in the case of spontaneous decay, the dephasing rate is simply related to the lifetime, the spontaneous decay lifetime of the excited state. Let's see, did I have another thing here? Yeah, okay, I'm coming to that. And sometimes then, of course, when we talked about dephasing, like when I imagined I had that electron spin and a superposition of 0 and 1, there wasn't any spontaneous decay, but there was dephasing. That was occurring because somehow the environment is catching on to whether the spin was up or down. So in many cases, the dephasing time is a much shorter time than the spontaneous decay lifetime. It's easier for the environment to find out whether the state is 0 or 1 than it is to flip it from 1 to 0. But that's not the case here, not in the case of pure spontaneous decay. And in fact, in that case, we say that the T2 is T1 limited. And in fact, it's a time which is twice as long as the spontaneous decay lifetime. T2 is equal to 2 T1. So now all this was assuming that nobody's detecting the photon. We traced out the state of the photon, but it's possible to detect photons. You can actually do an experiment if you're a skilled experimentalist, in which you surround the atom with photon detectors so that when a photon is emitted, you know it's been emitted. You can actually detect it. So of course, if you detect a photon, you know what happened. It means the atom was in its excited state, made a transition, it's now in its ground state, and that's why we were able to get a photon. But what if no photon is detected? You wait and you wait and you wait, no photon has been detected, you start to get suspicious. Well, in order for no photon to be detected after this long time, it must be that the atom is actually in its ground state all along, okay? So let's see if we can turn that intuition into equations. And what we expect to find now is that even though no photon is emitted, the way we describe the quantum state vector or the density operator is going to be changing with time, even though, so to speak, nothing happened, because as time goes by and we don't see a photon, the way we describe the quantum state has to change. So let's imagine we start out with some initial state of the atom. It's a superposition of the ground state 0 and the excited state 1. The photon field, the electromagnetic field, is in its vacuum. There are no photons around. And then this is the way we argued the state would evolve in a short time in which the probability of a spontaneous decay event, well, actually, whether it's small or large, we would describe it the same way, though I would like to consider the case in which it's small. That is, that there's the case where the atom was excited and it didn't decay, and that has an amplitude square root of 1 minus p times the original amplitude of being in the excited state of the atom. And there's also an amplitude square root of p for the transition from, oh, I think I lost a beta here, didn't I? Yeah, I should have a beta here. Because I'm saying that the beta 1, 0 made a transition to beta 0, 1 because of the spontaneous decay, which made the atom go from the state 1 to the state 0, while the environment went from no photon to 1 photon. And but now, like we did before, we can imagine that many such time intervals pass. And now there are a lot of different possibilities, and therefore there will be a lot of different cross operators, because in each of these little time intervals, I either detect a photon or I don't. I've got a photon detector. So when that photon appears, I know it. Every time the unitary interaction occurs between the atom and the electromagnetic field for some small amount of time, I imagine I'm measuring, projecting onto no photon or one photon. I'm looking to see if the photon is there or not. We weren't doing that before. We were supposing that the environment is unobserved. Now I'm going to imagine we're really making the measurement and I get some conditional state, conditioned on whether I see a photon or don't see a photon. And if there are altogether n possible time intervals, in each one of those, I could have either seen a photon or not. Of course, once you see a photon, there's just one atom, you're not going to see another one. Then now the atom's in its ground state and it's going to stay there. But you could have seen a photon in the first time window or the second or the third and so on, up to the last, the nth time window. Or you might have never seen a photon at all. You might have, after the many time intervals, n, you never saw a photon. So the Krauss operator corresponding to that case in which you never see a photon is, well, let's look here. That means that you always got the state 0 when you measured the electromagnetic field. Each time you did so, the amplitude for the state 1 of the atom got suppressed by another factor of the square root of 1 minus p. And that happened altogether n times if you never saw a photon. But what if you finally saw a photon in the kth step? Then it was getting suppressed by 1 minus p, this 1 component, was getting, or sorry, the state 1 for the atom was suppressed by the factor square root of 1 minus p, altogether k minus 1 times, because you saw no photon the first k minus 1 times, but then you finally did. So when you did, you picked up this additional amplitude of the square root of p. And in addition, the state made a transition from the excited state to the ground state, from the state 1 of the atom to the state 0 of the atom. So the Krauss operator for detecting the photon in the kth step is this one. It describes a transition of the atom from the state 1 to the state 0, but with this amplitude, a factor for not seeing the photon the first k minus 1 times, and a factor for finally seeing it at the kth time. And so again, if we consider the case of many consecutive time intervals, and we say there's some probability per unit time of spontaneous decay, then what happens when the no photon case, that cross operator is applied to the initial state? If after a total time t, we never saw a photon, well, that's just this m0, but now, as we've already discussed a few times, I can think of the square root of 1 minus p over n as going to e to the minus gamma t over 2, where gamma is the probability per unit time that the excited state of the atom decays to the ground state. So when we don't see a photon, the amplitude for having the excited state of the atom is getting smaller and smaller and smaller as time goes by. So really, if I wait a long time, so gamma t is a large number and e to the minus gamma t over 2 is incredibly small, I'm in effect doing an orthogonal measurement, although it's a destructive one. I don't wind up with the original undamaged state if it was in an eigenstate. In fact, I always wind up with the state 0 at asymptotically large times. But there are two possibilities. Either a photon was detected, and that can only be true if the atom was in the state 1, or no photon was ever detected, and that can only be true when gamma t is large compared to 1, if the atom was in the state 0. So in effect, I'm, with probability absolute value of alpha squared, getting the outcome no photon, and with probability absolute value beta squared, getting the outcome a photon was emitted. And it's the same thing as an orthogonal projection onto the basis states of the atom, the ground state, and the excited state. All right, so there's one more thing I want to discuss, which is Now I'm going beyond qubit channels, and I'm going back to a general discussion. What's the way in general which we should describe how density operators evolve with time? I've given you some examples in the case of dephasing and spontaneous decay of how to think about that, but what's the general framework? Now we know in the case of a closed quantum system, the evolution of a quantum state is unitary. It's determined by the Schrodinger equation. Or if I consider an infinitesimal time interval, when the time advances from t to t plus dt, then the state at time t gets multiplied by this operator, which up to terms which are of order dt squared, which I'm neglecting, is a unitary operator. It's just the identity minus I h dt. No h bar here. I got rid of h bar like I usually do. And so what's the corresponding equation for an open system? How do density operators change with time? Well, in general, it's kind of a complicated story, but we can write down a general form for the equation that describes the evolution of a density operator with time in the case where the time evolution is Markovian. I'll explain what I mean by that in a second. Well, I guess I'm explaining what I mean by it right now. What Markovian means is that the density operator, in this case, at time t plus dt is determined by the density operator at time t. You don't need any additional information to know how the density operator is going to evolve in the next microsecond. It's enough to know what the density operator is at time 0 to know what it's going to be at time 0 plus 1 microsecond. When we say non-Markovian evolution, what we mean by that is that what's going to happen between time 0 and time 0 plus 1 microsecond depends on more information than the density operator at time 0. I also have to know what the density operator was at time minus 1 microsecond or minus 2 microseconds and so on. It's not enough to know the instantaneous state to know how it's going to evolve in the next instant. And that type of non-Markovian evolution actually is quite common in open quantum systems, which you probably shouldn't be surprised by, because after all, how do we think about open quantum systems? There's a system and there's an environment. We don't see the environment. There's a unitary interaction occurring on the system and the environment. So you can think of some information as leaking to the environment from the system, but that information might come back again, all right? Or the unitary might, acting jointly on the system and the environment, might potentially undo the initial unitary or partially undo it. In that case, it wouldn't be enough to know the state of the system right now to know what's going to happen at right now plus 1 microsecond, because information which used to be in the system has gone to the environment and might come back again. But when I say the evolution is Markovian, I'm taking it for granted that when the information goes away, it never comes back again. You can think of the environment as an entity that forgets information so quickly that once information goes to the environment, I'm never going to see it again. So somehow it gets all mixed up in the many degrees of freedom of the environment, and it's very unlikely to ever return to the system. And that means Markovian time evolution is going to be a very good approximation. So what it means is that in each instant of time, I can imagine that there's no correlation between the system and the environment. They're not entangled at all. And then I can describe what happens from time t to time t plus dt as a completely positive map, because that's what we've always been talking about. The completely positive maps occur if the system and the environment are initially uncorrelated, a unitary occurs which entangles them, then we trace out the environment. But if we didn't trace out the environment, in other words, if at time 0 we still have an entangled state of the system and the environment, then we wouldn't necessarily be able to describe the map as a completely positive map, because I would need more information about exactly the nature of the entanglement between the system and the environment. And so the whole idea of Markovian evolution, which is a good approximation in some cases, like for example, for the case of atoms interacting with the electromagnetic field, the environment does forget very quickly, as far as the atom is concerned, in most cases, that a photon has already been emitted. And that means we can think of the environment as being refreshed in each instant of time and use our notion of a completely positive map to describe the evolution from time t to time t plus dt. And that's what this equation is saying. It's saying the evolution is Markovian, that to get the density operator at time t plus dt, you consider some completely positive map acting on the density operator at time t. And being a completely positive map, it has some operator sum representation, like shown here. And since the time has increased by just the amount dt, the density operator, which is the output from this map, will be the initial density operator plus some additional increment, which is going to be order dt. Now, as usual, we can think about this channel by imagining and recalling the discussion that we just had of the atom undergoing spontaneous decay, that somebody measures the environment. That's just a convenience, and it's not really that somebody is necessarily measuring the environment. That just provides us with the basis in which we can generate an operator sum representation. Well, we imagine there's some initial state of the environment, and there's some amplitude for that state of the environment to be unchanged. And then there's an amplitude for various transitions that could occur of the environment. Let's say it's initially in the state 0. It could go to the state 1 or 2 or 3, and so on. And for each one of those mutually orthogonal, perfectly distinguishable states of the environment, there will be some cross operator. So I have one cross operator, which is corresponding to the case where nothing is happening, that I'm calling M sub 0. And it's the identity plus something which is of order dt, because of course when dt goes to 0, nothing happens. A rho of t plus dt in that case is equal to rho of t. But then there's some correction of order dt, and I've, with no loss of generality, written this coefficient as a sum of a Hermitian operator and an anti-Hermitian operator. H and k are both Hermitian, but when I multiply by minus I, that makes this term anti-Hermitian, and this one is Hermitian, and I can take any operator and divide it into its Hermitian and anti-Hermitian part, and that's all that I've done there. But then for each one of the jumps of the environment to another state, there's going to be some corresponding operator, I'll call it a jump operator, acting on the system, like when the atom underwent spontaneous decay. But I'm going to scale these in a funny way. I'm going to put a square root of dt in all the non-trivial jumps where the index a is not equal to 0. And that's to make sure that all the jumps occur with some probability that scales with the time increment linearly in dt. So I can think of the jumps as occurring with some probability per unit time, just as we discussed in the case of qubit dephasing and qubit spontaneous decay. So here it is again, what the master equation looks like. And here's our expression for the jump operators. Now there's one more thing that we should note, which is we want this to be trace preserving. We're considering the case in which we don't observe the environment. We have Markovian evolution due to interaction with an unobserved environment. So our operator sum representation has to obey the usual normalization requirements so that the trace of rho of t plus dt will be equal to the trace of rho of t. We don't want the trace to change with time. So that means the identity is equal to the sum of MA adjoint MA. When I take M0 adjoint M0, I get a term which is I plus dt times 2k plus something higher order in dt, which I'm not going to keep track of. dt is infinitesimal, order dt squared is negligible. I want to find the terms which are linear order in dt. And those I want to set equal to 0 so that my normalization condition will be satisfied. Now, when you take M0 adjoint M0, the adjoint is going to change the sign of minus IH to IH. It's not going to affect K because K is Hermitian and H is Hermitian. And so there's a cancellation between the IH and the minus IH. So the H's go away. That just corresponds to the fact that to order dt, if there were no K, I minus IH dt would be unitary. And so if it's unitary, M0 adjoint M0 is equal to the identity. But there isn't any sign flip for K because it's Hermitian. So what I get to order dt from M0 adjoint M0 is I plus dt times 2k. But then I also have the contributions from all the jump operators, all the MA adjoints MA when A is not equal to 0. And each one of those is going to be linear order in dt. I arrange that by putting the square root of dt here. And then I will have LA adjoint LA times dt is what MA adjoint MA is equal to, or LA is this jump operator. And so since this normalization condition has to be satisfied up to order dt, because I don't want the trace to be changing with time, I can express K in terms of the jump operators, and that's what I did here. This expression in parentheses has to be 0. That means K is equal to minus 1/2 times the sum of LA adjoint LA summed over all the jump operators. So now I can write down the evolution law, the Markovian evolution, as a first order differential equation in time. That is, I can take the difference between rho of t plus dt and rho of t and divide by dt. That's the first time derivative. I've denoted it rho dot here. And the equation says that rho dot is equal to some linear operator acting on rho, which is sometimes called the Lin-Balladian. And what's in there? Well, we have a contribution from M0, which is going to produce a commutator of the Hamiltonian with the density operator rho, because when we have M0 in front of rho and M0 adjoint after rho, I get a minus IH rho from M0 times rho in order dt, but I also get a rho IH times dt from the rho M0 adjoint term, and all the other terms are higher order in dt. So that just gives me a commutator of the Hamiltonian with the density operator with the coefficient minus I. And that's just the Schrodinger equation for a density operator. That would be all I would have in the case of time evolution governed by the Hamiltonian H, unitary time evolution. And the rest of the terms describe the possible decoherence mechanisms, the jumps that could occur. And I have, as you can see, absorbed the probability of a jump into the normalization of these jump operators. So the probability of the jump corresponding to L1, for example, would be the trace of rho times LA adjoint LA. That would be the probability of a jump of type A. for each A, for the L1 jump, the L2 jump, and so on. So this describes, with the appropriately scaled probability, what happens when a jump occurs. And these other terms, well, we can see why they are there. They are the terms coming from the K in M0, in the M0 row M0 adjoint, where I've used our expression for K in terms of the jump operators. And so in other words, I have a K times a row, and I have a row times K here. And then I've substituted for K this expression in terms of the jump operators. And that is the general form of the master equation, which describes the Markovian evolution of a density operator. Sometimes it's called the Lindblad master equation. As you can see, it has the property of preserving the trace by design. In fact, what should happen is that if the trace isn't changing with time, then the time derivative of the trace should be 0, which is the same thing as the trace of the time derivative. So the trace of the left-hand side of this equation is 0. The trace of the right-hand side better be 0. And indeed, that's the case. Here I have h rho minus rho h, and because of the cyclicity of the trace of rho h is equal to the trace of h rho, and so those two terms cancel in the trace. And then if I take the trace of each one of these terms for each value of a, again, because the trace is cyclic, I can take LA adjoint over to the left-hand side here. I can take this LA adjoint LA over to the left-hand side. And so I have, and when I take the trace, it's the trace of LA adjoint LA rho, then minus LA adjoint LA rho from adding up these two terms and using the cyclicity of the trace. We've also seen by construction, and that's how we arrived at this master equation, that the time evolution from time t to t plus dt is a completely positive map. We enforce that by writing it in the form of a operator sum representation. And as we discussed in detail last time, that's really the most general type of completely positive map. Completely positive maps always have operator sum representations, and that's really all we assumed to construct this general form. Now, as we also know and discussed last time, a channel, and if it's not a unitary channel, any channel that describes decoherence, can be expressed in terms of Krauss operators in lots of different ways. In view of our isomorphism between states and channels, that's just the channel version of the statement that a mixed density operator can be expressed as an ensemble of pure states in lots of different ways. We talked about that last time. So the same time evolution can be exchanged. The jump operators, I can trade in these jump operators for others, which are related to the original jump operators by some unitary matrix, just like when we consider two different ensemble representations of the same density operator, according to the HJW theorem. There's some unitary matrix that describes how the original ensemble is related to the new ensemble. And I can do that for the jump operators in particular. So taking the same density operator and expressing it in terms of a different set of jump operators, sometimes that's called a different way of unraveling the master equation, and sometimes it can be handy to make use of that freedom to make master equations easier to solve, as is generally the case when we consider the different choices of Krauss operators to describe the same channel. You can think of that as arising from measuring the environment in different ways. So the different unravelings correspond to monitoring the environment in different ways, measuring the environment in different bases, and therefore describing the jumps in terms of different jump operators. So there's a lot more one could say about the master equation. There's a little more in the notes. about it than I'm going to do in class. We also have some discussion in the notes about the non-Markovian case, just so you don't think that Markovian evolution is the only thing that can happen in the lab. That's not really the case at all. So that's it. That's the end of our 4 lectures on open systems. Um, I think we've covered the essential things about open systems that you should know for this course and also for your general education and edification, which means we're ready to move on to a new topic. I've actually got a little ahead of myself. This is the end of the 5th lecture, and we've gotten to the end of the material that I anticipated would be covered in the first 6 lectures. Probably that's happening because I'm presenting the material using slides more quickly than I would if I were writing things on the blackboard. I guess that was inevitable. I've tried not to go too fast, and sometimes maybe it seems like I'm being a little long-winded as a result, but I probably have gone a little faster than the ideal pace. But you know, you have the advantage of being able to slow me down or speed me up or listen to me again, thanks to the lectures being recorded. So hopefully things are working out. And so that's going to be it for now. Next time, we're going to start talking about quantum entanglement in more depth, and in particular, what is it about quantum correlations, about quantum entanglement, which is really fundamentally different from correlations that we have in classical systems that will lead us into the notion of Bell inequalities and ways of testing quantum correlations to see that they can't be described classically. So that's a fun topic. Um, and we'll get into that next time. But in the meantime, I hope you're enjoying life and staying healthy. And I'll be seeing you next time. Okay, so be well and carry on. Bye bye.